Christopher Gomez, and today I'm going to talk to you about coastal landform and the coast in general, and that's part of the set of lectures between Kobe University and UMS in Indonesia. Let's start with a few elements. This is the coast of Comoros Island here. This is a photograph I took in 2006 when I was going to Kartala volcano. And the coast is really interesting because it's a volcanic island. You can see the very dark lava that makes the coast. This is another coast. This is the coast in Indonesia again, in Java. So this time I was working in 2007, just after the tsunami that hit the coast of South Java. We are just a few hundred of kilometers to the west of Parangtritis and to the west of Balon. And you have all those blocks here, which are a mix of different types of rocks. And you also have coral reef blocks that are part of that coast. So that's part of the Javanese coast, beautiful coast. You can see the spread of the sea on the coastline, and you have the forest, the coastal forest just in front here. Very, very nice place actually to go and visit. And those rocks, they are not all native to that place. Some of them come from further at sea, like the coral, and some of the processes that can bring them in are the storms, but there are not so many large storms in this place. The main process that transports those boulders, those rocks, are actually tsunami. So you can see here on the shore a lot of elements that are part of the tsunami. This is another place where I went in 2018. This is from actually an island. One of my colleagues at Stockholm University in Sweden, her parents have an island from generation to generation. So they own that island in the archipelago just south of Stockholm. And this is the coast as you can see it here. So you see it's very different from the two first coasts that we saw. This one is very rocky coast. It's the bedrock that you can see. And actually that coast, the water just in front of us is very, very deep. It's very weird, very funny to see huge ships and huge boats, ferries going across here. You can see actually once or twice a day the ferry that goes between Sweden and Finland, taking that route. And the reason behind this is because this was carved by glaciers. So the glaciers were carving that location, and they left those huge and deep, almost like glacier, way of the glacier that are now filled with water. And the top of the rocks that you can see also around here. So I'm going to put the pointer. Oh, I'm going to put the pointer if I can. So the rock that you can see here, you can see they are very well polished, and all of those are granite, and this is part of the bedrock as well. And this was polished, of course, by the glacier the same way. And finally, this is another coast. I just went a couple of months ago that's the coast of Sendai in Japan. And it's taken from UAV this time. And we are just north of the main Sendai plain, near the main harbor, near the port. And we were doing some UAV work there. And this time it's a very different coast again. This time it's only fine sand. So if you compare those four different coasts, like you can compare that one as well. And when you look at this, or you look at this coast made of a lot of lava, quite hard rock, but still mixed with other material. And here you have other type of coast, which have a mix of block and sandy coast. And here you have a purely hard rock coast. And on that one is like pure sand. So because we are at the interface between the sea and the coast itself, between the material on land, you find your way with a lot of different type of coast influenced by both sides, either by the sea process, the wave processes, and also the material which is there on the coast, and the material which is brought up or eroded by the waves. And those are the main configuration we're going to talk about today. So what are the objectives and learning outcomes? So I would like you to know what are the different geomorphic processes at the coast. I would like you to be able to differentiate erosional and depositional coasts. So coasts that erode against those that deposit material. Erosion, to give you an idea, is Shinshoku in Japanese, erosi di bahasa Indonesia. Yeah? And depositional is like when you have the opposite of erosion, taiseki. So different way of working. And then we'll see the influence of the human factors on the coast. And these different objectives come as learning outcomes this way, where you will know how to relate different geomorphic processes at a range of spatial and temporal scales. You will know the nature of the different waves at the coast. You will be able to relate the learning from this class to landforms in your own country, because I'm going to talk to you about processes in general, and then you'll need to relate those maybe to what you can see around you. So ocean, seas, and the earth. So the ocean, they refer to the largest bodies of salty water. Seas are subdivision of the oceans that are partially enclosed by land. So when you have a huge mass of water, that's going to be an ocean. And then whether you have some smaller places that are connected to it or not, those are going to be seas. And the Gulf are smaller arm of an ocean. So you have the Gulf of Mexico here, what we call the Bay of Biscay, but there is the Gulf of Gascogne in that place. So you have the Gulf of California, so the Gulf of Guinea. So you can see those roundish shape that enclose or semi-enclose portion of the ocean. And then the bay is a small indentation of the coast connected to the ocean, sea or Gulf. So it's like the Gulf, but a smaller one. Those are the rule of thumbs to understand the different wording and the different meaning of those. But at the same time, you just need to remember which one is which, because people will have like, those are somehow very general rules. And am I not recording? I am recording. Okay, perfect. So all oceans, seas and gulfs are interconnected, except some inland seas. So you have a few specific inland seas, and they have the same basic chemical composition. Interaction among atmosphere, seawater animals and sediments, and a myriad of organisms is part of what we call the ocean. So it's not just water. And the ocean water is a solution. So what do we mean as a solution? It means that in the water, you have in solution different elements. So the salinity refers to the concentration of dissolved solids in water, in seawater more exactly, varying between 34 and 37 parts per thousand. Then you have what we call the brine. The brine is the water that exceeds 35 per thousand parts of salinity. And then when it's even more actually like denser, I would like say, when the water is brackish, brackish is the water that is less than 35% of salinity. So you have the salinity level, you have brine 35 and more, and you have brackish 35 and less. So brackish water will usually be found in places where you have estuaries, where you have connection with the land and the water from the land at the end, the exit, the mouth, of a river is located. The nature of coastline, the processes that shape the coastline. Well, at the global scale, the continental scale, very large scale, one of the important elements, if not the important element, is the eustatic change, which is the water level fluctuation that occur when uplift or sinking is occurring. So we talked about this in one of our early lecture. We explained that plate tectonic and plates are floating. So when those plates are loaded, they tend to go down, and then unloaded, they tend to go up. And this, of course, when you have a continent on top of your tectonic plate, this will have impact on the coastline itself, because the coast is going to move. And this happened during different periods. And let's say, looking at the latest period, during the glacial period, the ocean water will be lower. So you also have the large volume of water which is stored in the ice sheets, so that the coast will also extend. And during the interglacial period, glacial ice melt into the ocean, and then the ocean goes up. And that's another of the processes that comes in. So some of the areas that were sub-areas exposed, for instance, so river extend onto the platform, which cut canyon into the shelf, depositing during major low ocean level. So when you look at your map, let's say after this lecture, you're going to have a look at your favorite Google map, Google Earth, and you look at underneath the water. This is not usually where we go when we look at Google Earth. You're going to see that you're going to have the continuation of rivers underneath the water. And if you go to the south of France, for instance, you will have the Rhone River, and you will see the Rhone River continuing into a canyon right into the sea, into the Mediterranean Sea. And you might wonder, why is that so? Well, again, in the Mediterranean Sea, it's quite specific because the sea was completely shut at some point, so water evaporated. But also with glaciation, when the water level goes down, it means that the coast is extending. And when the coast extends, then the rivers are going further into the sea, and they can carve their pathway like they do on land. So you have channels. And once those channels are carved, if the sea level goes up again, sorry, then you're going to have some buried channel. So there are two types that we recognize. One is the Ria. The Ria is a large river valley that was flooded when the sea level rose, and they are very common along many coastlines. And we have also a fjord. A fjord is an ice formed through that becomes flooded when sea level rises. For the fjord, you can go to New Zealand, you can go to Southern America, you can go to Norway, and you will find a lot of those as well, where you can see those very large valleys being actually flooded today with water, with seawater more exactly. And then when you look at it at a smaller scale, you realize that actually the coastline are not regular either. Those coastlines actually are changing over time. And for those coastlines, one of the reasons behind those are the tides. So the tides, they are regular and predictable oscillation in the sea level of the world ocean. They are related to the pull of gravity of the moon and the sun due to the rotation of the moon and the earth. They create a centrifugal force that pulls tide on both sides of the earth. Tidal range varies according to the shape of the coastline. So now, if you look at the oscillation of a body of water due to the force of friction from wind blowing on the surface, so surface of water, We're not talking about tsunami here, just from the surface. The wave formation involves wind strength, wind duration, and wind fetch, or the distance of unimpeded airflow. All the waves appear to be moving horizontally. They are just rising and falling disturbances in the water. So they consist of variable, measurable component. When you look at a wave, you have the wave crest, which is a high spot of a rotating wave, of an individual wave, sorry. Then you have the wave base, which is where the column of water rotating disappears. And you have the wave trough, the wave length, amplitude, and the wave height. We're going to see a graphic in a second. So that's how the wave look like. So you can see here at the top, you have the wave crest. And right here, you have the wave trough. And all of this is being created, as I was telling you a second ago. It's not only a movement of the surface, it's actually the rotation underneath. And that rotation of the surface is created here by the wind blowing. The wind blows and makes the water rotate. And this rotation is going to continue further down in the water column. And that is also going to create actually some movement in the sediment when it's not too deep. And once you get close to the coast, then those movements will become more complex because they do interact with the geomorphology, with the local topography. And when you are at the coast, you have this in this area, wave that can become breakers. So when they do this snake type of movement, and that location afterwards where everything breaks and gets on the shore is called the surf. And then at the top here, you have the beach. The beach is divided again into a different set of components, but that's for another time. So near the coast, seafloor slopes upward and water depth becomes shallow, so that the wave base intersects with ocean bottom. The wave height increases and speed slows. Waves continue to advance, crowding into the force, showing each wave's height to increase until the wave crash as a breaker. So when you think about the wave at the shore, the wave and shore interaction depends on a set of components, which is the shape of the coastline, the direction and seasonal variation of the prevailing winds, intensity of the wave, the tidal range, and the nature of coastal sediments. So the shape of the coastline. So imagine you have some waves coming in, and those waves encounter a perfectly flat and regular coast. So they will arrive on the coast as a straight line. Now, you remember at the start, I was talking to you about gulfs and bays. Imagine that you have a bay. So like this semicircular shape, coastline. When the waves arrive at the bay, they are going to go around and shape on the bay, right? So the center part will have usually more velocity than the outer part, and you're going to have actually modification of the direction of the waves reaching the shore, but you will also have across the bay different level of energy distribution, so that the sediment and the wave interaction with the sediment will really depend on where you are in the bay. For the same reason, when you think about the wind and the prevailing wind's direction, if the wind blows across the coast, towards the coast, or like north-south or up down the coast, you're going to have, of course, different wave directions. This means that those wave direction changing will have different impact on how the wave arrive at the coast and how it's interacting with the coast. Then you have the intensity of the wave and the tidal range. So the energy which is actually arriving at the coast, but also how much variation you have every 6 hours in your tides. So if you have a micro tidal and it's not moving much, or you have actually very huge tides, then of course the impact at the coast would be very different. Think about what we were looking at just at the start when I was showing you the photograph of the coast in Sendai, where you have only sand. If you have some interaction of the wave when you are at low tide, some erosion, whatever it's happening there, once you get to high tide, there is such a large difference in the area which is going to be impacted that you're going to create other type of landforms at that place. So it's very important actually to consider the tidal range as well. And then finally, just to go back to that question of sand, the nature of the coastal sediment. If you have, like in Sweden, a very hard rock coast, or if you have, like in Japan, what I was showing you in Sendai, a sandy coast, then of course the processes would be very different. And it also means that the use of the wave energy is going to be different. The energy of the wave will be spent also in moving the sediment. So when you have coarser sediment, those coarser sediment will absorb in some way. It will use, not there is no absorption, but they will use some of that wave energy to get motion as well. When you have hard rock, it's just reflecting. And this is actually one of the main problems when you think about coastal protections, because a lot of the world of the man-made coastal protection are made of concrete. So we have concrete walls that replace sandy shores and other type of shores. And in that case, we actually reflect the energy of the waves. So we are increasing the wave energy which is available. In some places, so the sediment moves freely along the straight coast, where in other places, the sediment will be actually trapped in some bays and other crannies, let's say crannies along the coast, meaning that you're going to have actually along those coasts some variation, even if you have the same wave, the same tide, based on the local geomorphology, which is going to play a very important role. Now, when you look at the sediment transport along a very simple coast, and we can take only sand in that example here, you have two different currents you have to think about. There is the longshore current, which is in red here, going along the shore. And then you have the wave with the wave crest that shows actually how the wave arrive at the coast. And here they are at an oblique angles, not straight to it. And those will influence and control some of the processes that transport the sediment. So the longshore currents, they flow parallel to the shore and forms when wave approach the shore at an oblique angle. So imagine it's like your hand goes like this. So all of this is moving. There is very rarely a perfectly straight perpendicular angle. So most of the coasts have those longshore currents. Then you have the longshore drift, which is the movement of the sediment that occurs along with the longshore current. Then you have the beach drift, which is the transport of sediment in a zigzag pattern. This is what you have here. So this is much more smaller scale here. And then you have the littoral drift, which is combined processes of the longshore drift and the beach drift. And once you know that, you understand why we have those very long walls sometimes coming at sea that they use to trap the sediment. It's to stop actually from the sediment moving away from one location or another. It is a natural process. We should let it happen. But most of developers who are not geomorphologists would not agree with that. Most of the practitioners want to keep some stability in the landscape. Imagine if you buy a house by a shore, you don't want the shore to disappear within a couple of years because of some bad storms. You make sure that your investment will stay. So one of the reasons why we actually do these kind of things is to keep things where they are. When we have erosional coastline, it means that the coastline is dominated by erosion processes. the most coastal erosion occurs as waves on the shore. So the wave will be the main agent of erosion. And usually it's going to create a variation of headlands and pocket beaches, like you can see. And that kind of beach here, those pocket beaches, they are creating then local small bays. And the headland then is a landform of more resistant rock that juts into the ocean and is surrounded on three sides by water. It tends to form a long shoreline with bands of rock of alternating resistance. So resisting rock, not so hard rock. And those can occur in a variety of different geological frames. The easiest one to understand would be the rise of some rock layers that alternate hard and soft rocks. So when you look at those erosional coastline, not in plan form anymore, but as cross-section, on the shore, you will have actually typical landform that will be created. So when you think about this, you look at this graphic here, we start with non-eroded rocky shoreline first, then we go into B, formation of vertical bluff, C, waves that cut notch in the base, and then the overhanging cliff collapse, and then you have the sea cliff retreats and erosion at the bottom. So these kind of processes move the coastline. And if you have actually an erosion coastline, which is going to get rid of that extra material underneath, then the coast will retreat progressively. This kind of work, this kind of operation, this kind of process will be visible when you look at shoreline, let's say, in southern England, where the coastal cliff are now retreating very fast. And this is being emphasized. It used to be like this before. So the coastline was already retreating. When I was young and I was in Paignton in South Devon, the coast was retreating. But because I remember they were telling us, don't get too close, don't walk underneath the cliff. But today, this is making it worse because of climate change. And when you look at those processes and you get them one after another, then you have this kind of cascading set of processes. You have the old cliff first, and then the marine terrace and the new wave cut bluff. Can you remember the lecture I was doing in another class, and you should have been taking it if you're part of this class yesterday about natural hazard? I was talking to you about the factor of safety, and linked to that factor of safety, we were discussing some example across the world. And one of the entry photograph I was showing you was this in California, La Conchita earthquake, not earthquake, La Conchita landslide. And La Conchita landslide occurred actually in the old cliff. You have the old cliff, you have the shore, and then you have the ocean. That old cliff is not active anymore, but that's where actually you had that landslide coming out. So, and this is the kind of configuration that you had. So when you have a rocky coastline, you're going to have actually other type of landforms that occur. Let's say you have those headland again, and those headlands are getting eroded. You're going to have those headland like retreating slowly and leaving actually some lumps of rocks that remain in between the different bays. And at the end, you're going to get this kind of landform. I say at the end, it's not the end. It's one of the steps in a myriad of processes. And these kind of things can lead to a lot of different erosion landforms on the coast, like sea caves, sea arches, sea stacks. And I'm going to go back to the first slide for a second to show you one of the sea arches. So that is exactly what's happening. So you have some hard rock there, You have that bay here where you had like some rocks that were a bit softer. This is an arch. And this coast here, this is a retreating coast. Okay, so that's how it looks like. And this is one part of those processes. Now, if we look at the opposite, this was erosion. Let's consider now deposition of coastlines. So first, when you think about progradation, it's the process by which coastline extend outwards into the sea, into the water through deposition. Beach are dynamic places where sediment is deposited by waves, beach drift, and winds. The transition between the water and the landmass consists of exposed, unconsolidated sediment that can usually range from sand to cobbles. So when you think about the beach, it's not actually only sand, fine sand, beautiful white sand. You can have a lot of different beach. You can have beach made of actually smaller gravel, sand and gravel, mixed sand and gravel, and also cobble beach. So a wide range of different types of beach. And if you look at the geomorphology of those depositional coastline, typically what you're going to see, and I was telling you, remember one of the first slides, I was showing you a beach, I was telling you there are different divisions. It's not only beach, we have different elements on that. And here we go. So when we have this kind of beaches, we're going to have at the back sand dune that can have underneath different type of material. That can be some hard rock, and can be still sand. Then we're going to have at the top here what we call the back shore. And the back shore is separated from the foreshore by the berm scarp here. And the berm scarp is the high water line of high tide. That's how we define it. And on that foreshore, we can also find the low water line of the low tide. And we can use that to actually measure also the present, but also paleo, if we have some beach that are conserved, the range of the tides in the past. And then towards the sea, then we have what we call offshore area. And at the base, at the start of the offshore area, we can find sometimes also an offshore bar. So the beach components based on their position to water are offshore, which is the submerged zone where waves break, the foreshore, which is influenced by rise and fall of the tides, offshore bar, which is the submerged reach where wave velocity is low. And then we have the berm scarp, which is the high water line of the beach, and the backshore, which is a relatively flat area covered with water only during very severe storms. So what are the coastal landforms associated with it? So the coastal landform associated with it, we have the depositional coastlines. The longshore current carries sediment-forming features like spits and bay mouth pad. A spit, what is it? A spit is a linear bank of sediment extending into the bay. A bay mouth bar is when a spit extends entirely across the bay. A lagoon is created when the bay is enclosed. And finally, a tombolo is created when the spit grows to reach a large sea stack or island. So here we have some example here. So we can see that's a spit here. You see that small band of land, that small band of land usually made of sand and sediment, gravel, and that extends from the main beach here. When this is actually closing body of water, it's going to be the bay mouth bar, and those bars, those spits that enclose those bays, when those bays become close, they become lagoon. And those lagoons then can be stopped at what we call, when they are not connected to the land, barrier islands. And to create those features, the longshore current is going to be very important here. And when the longshore current transports sediments and the sediments create a bridge between what was an island and the coast, then we have the creation of what we call tombolo. And the tombolo is created by those movements of wave refraction against the former island as well, so that the sediments are pushed against one another. Coastal dunes develop because the supply of sand along the beach can be high. A foredune develops due to the shore vegetation that traps sand blown by the wind off the beach and gradually forms a linear ridge, not a linear. Here it should be linear ridge or dune. Switch the A and the R, sorry. Transgressive dune fields form when the supply of sand is especially large and the winds are constantly strong. These dunes transgress or advance inland and bury all the surfaces. Then the creation of barrier islands. And we're going to take 5 minutes break, and we're going to be back after the break. And we are back after this short cut. So you shouldn't see much if you are watching the video online, because I stopped the recording. So barrier islands are accumulation of sediment parallel to the shore formed by the waves, tides, and winds. And they're likely to form on broad and gently sloping continental shelves. And they are usually related to the supply of sand. And behind those barrier, you have the formation of lagoon, as we saw earlier. So this is the configuration, basically, how they evolve, where you're going to have first sediment which are accumulating behind it. So those fine sediments that accumulate there, you have fine sediments because the barrier, that's why they have those names, they also protect that location from the wave energy. So smaller sediment can settle, and through that settlement, through this sedimentation, you have the creation of mud floods. And those mud floods can then become marshes as well. Once they have accumulated enough, you have plant vegetation that start on top, and you have those large marshes that are created. So those are very flat area. And they used to be actually much more common across the world. Like if you think about Tokyo Bay, for instance, you don't think about the mud flat of the marsh, but because the city extended on the sea, they got rid of those locations. But Tokyo used to have extensive mud flats and marsh all around the city. And then when you think about the depositional coastline, you have also other type of land formation. And one of the processes that create lands are coral reefs. So coral reefs are landforms that evolve through the growth of living organisms. That's why it's a bit special. It's not sediment falling, this time it's something growing. And those living organisms are coral, and that excrete the skeleton of calcium carbonate that accumulate into limestone deposits and then go up. It takes a bit of time before you can look at it as a limestone deposit, but it's still actually forming those landforms. And the deposit grow larger when one generation of coral dies, and then you have the new one on top, and that's how it goes. You have certainly heard about coral reef and coral reef issues because of climate change and the sea temperature changing. So coral reef and corals usually grow best in tropical waters that are warmer than 20 degrees and that are free of suspended sediment, so clear, clean water, and are well aerated. So you need a lot of actually oxygen in the water. But when you change the chemistry of the water, when you change the temperature, then you get, they are actually quite sensitive to temperature change, and you can have a coral bleaching and the death of coral. So the whole coral growth just stops and the coral dies. And coral reef, when they develop, actually can create some very peculiar landforms. A coral reef formed in 3 distinct settings: as a fringing reef on a shallow platform, as a barrier reef, or they can also create and develop as an atoll, or a semicircular reef most closely associated with the degradation of volcanic islands. So this is the process here. You have first the volcanic island, which is formed. That volcanic island is going to erode away, and then you get only actually the coral reef separating the island that remains. And still, that part in the center is going to continue eroding until you get a shallow lagoon, and just that coral growth that continues from that atoll. So you have in the Pacific a lot of atoll that looks like this, with very small islands sometimes, or not at all. And those are usually related to past volcanic activity that then disappeared. And finally, the last element that really comes at play are the human interaction on the coast and the coastal engineering, the structures that are built on the coast. They are usually sold as to maintain, to improve the flow, the trade in traffic of ports, but they have actually a lot, most of the time, negative impact on the processes that occurs on the coast. Those are linked with also the development of artificial sediment production, like the stabilization, nourishment of beach. It means that we bring sand to actually feed the beach, and we use berm and other features to keep the sand on that beach, but those are not natural and not in equilibrium with the waves. So it's really a battle, a lost battle most of the time. So we construct seawall, revetments, and other structures. So if we are in countries like in Western Europe or in the United States, where there is a lot of space, arguably, you can argue that the land should be allowed to retreat or to advance and move freely, because people don't have to be there. But if you're in Indonesia or in Japan, where the coastal plain is really much all there is and it's very, very short, it's really hard not to have actually those protection, those coastal engineering structure, because there is just no space to go. And in Kobe, where I live now, right now, you have actually a lot of islands that are man-made islands, and not because people had to go and make those islands, it's because there were no other space, and that was compulsory to have those. The airport of Kansai Airport is also on a man-made island, just because there is no other space in other places. So it's a difficult problem most of the time to decide whether a coastal structure is good or not. It definitely has negative impact on the environment and the geomorphological evolution. But there are places where we can have actually other alternative solutions. And there are places like maybe like in Japan or like in Indonesia, where those alternative solutions are not feasible for a variety of social and socio-economic reasons. And if you look at some of how they look like, you can see here those different berms and groins that are stopping the sand from moving. There are walls across the shore. You have the creation of jetties that can also open water in a channel, like here. So you have your longshore. The longshore creates those barrier island, for instance, and you need actually that barrier island to be open, because one of the negative aspects is this lagoon here, if it's closed, and your river is flooding, it's going also to flood the lagoon and extend the flood in that lagoon, which is maybe not what you want. So there are also openings that are man-made opening like this, but also for port and recreational activities. On that photograph here, you can see a small boat is going across it. So if you want to go from the port down or up into the sea, you need to have those openings as well. And then with global climate change, with the rise of global temperatures, which is also due to human activity, you have the melting of ice, and then not ice on the sea, the melting of ice on land, which matters for us. And this is actually modifying the coastline as well. So you have on North Carolina here, the shore below 1.5 meters, 1.5 and 3.5 and above 3.5 meters. So let's not consider 3.5. 3.5 can still be flooded when you have a big storm. And that's not a big storm combined with a high tide, and that's enough. If you have a storm or a typhoon, over there are tornadoes, not tornadoes, cyclones, sorry. Cyclones that go up that coast, and that's enough to flood also up to 3.5 meters. And what is interesting here is that you have huge areas of 1.5 meters and less. So those huge areas, actually, you have like 30 kilometers here. So we are talking 30 kilometers here, 30 kilometers here. It's not a small island that are set to eventually be either eroded or at least flooded because of climate change. So in conclusion today, coastal landforms, they are certainly the product of the interaction of land and coastal processes. The wave regime dictates the general micro and mesoscale landforms, while the general configurations of the coast are dictated by long-term and large-scale evolution, like isostasy and tectonic activity. A coastal landform can be divided between a depositional landform and erosional landform, and in the Anthropocene, humans have an important effect on the coasts as well. So I hope this gives you a very good overview of the different type of coast that we have and how those can evolve. For those of you who are interested in the math and the physics behind it, there is plenty of work that has been on that, but today was not the objective to explain to you from that perspective. I just wanted you to have an understanding of how systems and how it works in general. Thank you.